Good evening everyone. Welcome to AS Online. Today we are going to see an important topic, that is synchronous machines. In that one important topic I am going to give and some questions on synchronous machine for RRB JEE related. Okay. Now the topic is this one. Conditions for parallel operation. Now one important topic in total synchronous machines is parallel operation of alternators. So very important it is. So regular questions we have in every examination from parallel operation. So in that first important is in order to operate any two alternators in parallel, important is what? First we have to check conditions. Before connecting directly, suppose there is one alternator, another alternator we are connecting in parallel with that. So before connecting in parallel with that, we have to check some conditions. So what are that conditions? So that we are going to see today. Okay. Now in that, before going to conditions directly, first of all, what is the need to operate alternators in parallel? Like that we also have transformers in parallel. What is the advantages, or what are the advantages to operate in parallel? Tell me, what are the advantages of operating alternators in parallel? Yes, not only alternators, transformers advantage also same, that is mainly with parallel operation of these generators or alternators, we can get easily the load sharing, or suppose continuity of load. If you talk continuity of load, suppose there is one alternator supplying some load, no parallel operation. If there is any problem occurred in that alternator, now supply is disconnected to load also at the same time, so there is no continuity to the load, sir. But if there is a parallel operation of alternator, suppose two alternators operating in parallel, one alternator got some problem, still you can maintain some power to the load from other alternator for some time. Even overloaded condition, we can operate that alternator by providing some extra cooling to the alternator, some extra cooling. So generally what happen if alternators or transformers overloaded, they may damage. But at the same time, if you able to provide a good cooling system to the same alternator, overloaded alternator also you can operate safely, no problem. Okay, that is important here. Like that, one advantage of parallel operation of alternators is load sharing we can done easily. Suppose there are so many alternators, some alternators suppose gets overloaded, we can distribute the load to some other alternator. So load sharing is well maintained. With that proper load sharing, mainly we can achieve higher efficiency of alternators. By properly maintaining loads, we can get high efficiency. So this is one advantage. Like other advantage is continuity of supply. We can maintain continuity of supply to loads. Even one alternator is damaged or problem or faulted, still we can maintain supply to the loads from other alternators. That is one advantage. Efficiency increases. Okay. Next, one more advantage of parallel operation is reliability. Reliable power supply. Reliable. So means when there is number of alternators working in parallel, in future some load added, you also add some alternator or some generator in parallel with existing system. You no need to remove that existing system. Suppose if there is no parallel operation concept, then what we have to do? Suppose there is one alternator supplying some load. In future some load added. If there is no parallel operation, that alternator capacity is not sufficient for the load, then you need to increase the capacity. How? By using some other generator, not same generator, no? That capacity is over already. Means that alternator not suitable for the increased capacity. Now you need to install new alternator with higher capacity. When there is no parallel operation it is. This is not reliable. Reliable means when loads are increasing, you also add alternators in parallel. So whenever you add small alternators in parallel, that is reliable. That is not high cost. Okay, cost will reduce, maintenance will be reduced compared to single alternator of large size. Okay, that's why some advantages we have. And the one more main advantage of operating alternators in parallel is we can maintain a constant voltage at the loads. That is the important thing here. So we are getting constant voltage and frequency to our house, to our home. How it is coming? How we are getting that constant voltage and frequency? If you take the power from single power plant or single alternator, you don't get constant voltage and frequency continuously. But we are getting constant voltage and frequency because we are collecting from busbars, grids. grid will maintain. Grid is interconnection of so many alternators. That's why when there are number of alternators working in parallel, if any alternator shut down also, it won't affect the load side. If any alternators suddenly fault, still it won't damage the loads. So loads will maintain almost at constant voltage and frequency. That is the main advantage of operating alternators in parallel. Now let's see what are the conditions to operate in parallel. So for example, considering there are some alternators working in parallel here. There are some alternators working in parallel. This is our bus bar. Here existing system it is. Existing means some alternators are there here. In this region, there are some alternators. Now suppose this is our new alternator. This is our new alternator. We need to operate this alternator in parallel with existing system. Then what are the conditions we need to verify? See this. So directly we should not connect alternator to bus bar. So first we will check the conditions, then only we connect it. So here we will have switches, just like switches we connect, directly we don't connect it, switches are placed here. Now across that there are totally 3 conditions here first, that is first condition is, first I will write the condition, see this. First condition is voltage rating. Voltage rating of 2 alternators must be same to connect in parallel. 2 alternators. Suppose if you are connecting with bus bar, if bus bar is having some voltage V and F, let voltage is V and frequency is F. Now this alternator also should generate same magnitude of voltage, that is if it is 400 volts, it should also generate 400 volts at that time. Now how to verify that voltage rating condition? First condition is this: voltage rating of alternator must be same as bus bar voltage rating. So whatever is there here, same voltage should be there. How to verify this condition? So to verify this condition, simply we put one voltmeter across the bus bar and alternator. So one voltmeter we place. Now what should be the reading of this voltmeter in order to say that both are at same potentials? 0. If this voltage, bus bar voltage and alternator voltage ratings are same, then what is the difference of these two? 0. So voltmeter will show 0 reading here. Voltmeter shows 0. So like that easily we can verify this condition. Suppose voltmeter is not showing 0. It is showing other than 0 means the voltage of these two systems are different. Alternator, bus bar voltage is different. Now which one we have to adjust so that the voltmeter will become 0, voltmeter reading will become 0, such that both are said to be at same voltage ratings. So which one we have to adjust here? In order to change the voltage rating of alternator, generally we prefer to change the excitation of alternator, maybe increase or maybe decrease. Excitation of alternator. So whenever excitation changes, flux changes, voltage will change here. So it is easy for us, excitation variation, in order to verify this voltage rating. Okay. So the voltage rating can be verified by voltmeter across the two systems. If voltmeter is not showing 0 reading, then adjust the excitation of alternator up to the voltmeter indicates 0. Like that easily we can adjust this. So this condition is easy for us. But next 2 conditions are important. What is the next 2 conditions is? Second condition, frequency of alternator should be same as that of bus bar frequency. Frequency of this alternator should be same as that of bus bar frequency. Now how to verify this condition? So frequency condition and third condition is phase sequence. Phase sequence of alternator should be same. Phase sequence of alternator should be same as that of bus bar phase sequence. So these 2 conditions we will verify with one of the method we call synchronization methods. These 2 conditions we will verify by using synchronization methods. Synchronization methods. These 2 conditions, frequency and phase sequence. Okay, we will see what is that synchronization method, how we will synchronize alternator with bus bar. So before that, suppose frequency of alternator is not same as that of bus bar frequency. They are different. So then in order to make both equalize or same, which one we have to adjust in the alternator? This mechanical input or steam input or mechanical input or turbine input. So this turbine input we have to adjust, speed we have to adjust such that the frequency of both the systems must be same. Voltage rating can be adjusted by excitation and frequency of alternator can be adjusted by prime mover input or mechanical input. Next, third one is phase sequence. So two conditions we verify by these methods. We will see the methods again. Now phase sequence of alternator is not same as that of bus bar sequence. Suppose phase sequence is not matching, then which one we have to change in the alternator to get the same sequence? Suppose alternator rotating clockwise right now, and bus bar sequence is RYB, but alternator sequence we are getting RBY, for example, different it is, they are not same. In which direction we consider? Rotor is rotating clockwise direction. So if you want to change the phase sequence of alternator, what we have to do? Reverse the direction of rotation here simply. Clockwise it is rotating previously, then sequence is RBY, so phase sequence is not matching. Then adjust or reverse the direction of rotation of this turbine or rotor, so that sequence will change automatically. So phase sequence can be adjusted by interchanging direction of rotation of the rotor. Frequency can be adjusted by changing speed of the turbine. Okay, so these are the three conditions we need to verify before connecting this alternator to bus bar. Suppose all the conditions are verified, all are synchronized, all are same as, that is, all the conditions satisfied such that bus bar and alternator having same, then close these switches. Now alternator connected to bus bar, then it will operate however other alternators operating in parallel already, it will also operate now. Okay, now let's see what is the synchronization methods, how to synchronize and what are the methods we use for this. Right, synchronization methods. Synchronization methods. Now in the synchronization we have mainly two methods we called. First one is lamp methods and synchroscope. So synchroscope is an instrument we use to verify to compare the frequency of the two systems directly, and here phase sequence will not come directly. Okay, but anyhow we will see only lamp methods. Synchroscope is an instrument method. Directly by using an instrument we will compare the frequency of two systems, bus bar and alternator it is. So frequency directly easily will come in this method. But lamp methods important. Using lamp methods we will get both phase sequence and frequency at a time. Okay, so let's see in the lamp methods there are two types again in the lamp methods. First one is 3 lamps equal bright, 3 lamps equal bright or dark, This is one method. And second method here is 2 lamps equal bright, and 1 lamp dark. Now why these two methods is, actually one method is enough, but in first method we will get one drawback. To overcome that drawback we go with second one. So second method is best one, easily we can identify here and we can confirm both operating at same phase sequence and frequency using second method. So both are we use, but first method drawback is there, that's why second method is preferred method. Okay, now let's see the first one, 3 lamps equal bright or dark. First one is 3 lamps equal bright or dark. 3 lamps equal bright or dark. So what we need to do here is we have to take 3 lamps. This is the bus bar 3 phases, bus bar 3 phases, R phase, Y phase, B phase, and this is alternator 3 phases, previous diagram only, here alternator is there. So this is let RY be, and alternator R dash, Y dash, B dash, alternator 3 phases it is. Now we have to connect 3 lamps here such that L1 is connected between RR dash, L1, L2 is connected between YY dash, and L3 is connected between BB dash, okay, like this, L1, L2, L3. So 3 lamps we have to connect L1, L2, L3 between RR dash, YY dash, BB dash, and check for this condition. 3 lamps should give equal bright at a time or equal dark at a time. It is not like one is bright, this is dark, and this is little more bright, not like that. All the 3 lamps should indicate same brightness at a time, and all the 3 lamps should indicate same darkness at a time, any one, because we cannot say that which one will come. Which one will come once you connected, we cannot say all the lamps may show bright or all the lamps may show dark. So when the lamps will show equal brightness is, see here, suppose RYB, bus bar 3 phases, R, Y, B. At this instant, like this they are present. Now whenever we connected the lamps at that instant, R dash, Y dash, B dash also, for example, exactly in phase with the bus bar Y dash, B dash. So exactly in phase with bus bar. Okay, alternator 3 phases also in phase with bus bar. At that time lamps are connected. Then L1, so this is L1 here, L2, L3, L1, L2, L3. 3 lamps connected like this. Now what is RR dash? In phase. So what is potential difference? 0. So whenever potential difference across the lamp is 0, the lamp will not glow here. Okay. Then what is the position of these 3 lamps? L1, L2, L3? Dark. So this position is the dark position of lamps. All the 3 lamps are dark here, equal dark. All are same darkness because no potential difference. So whenever the 2 systems, that is bus bar and alternator, having in phase, exactly in phase, then this is the position. So you may get this or you may get brightness also. So when we get brightness is, for example, bus bar 3 phases are like this, RYB, R phase, Y phase, B phase. So at the instant of lamp connection, the alternator 3 phases, for example, they are exactly out of phase, like this, R dash, Y dash, B dash, like this connected. Now where is the lamp 1, L1? L1 is between RR dash, L1, L2 is between YY dash, L3 is between BB dash. This is L3. Now like this the 3 lamps are connected. Now what is the potential difference? If it is positive maximum, this is negative maximum at the same instant. So we may get any position, we cannot say that whenever lamps are connected you will get bright or you will get dark. That depends on the position of these phasors inside, where these phasors located. Is the phasors of 2 systems are in phase or out of phase? If it is out of phase, maximum voltage difference we get or maximum voltage we get across the lamp. That's why this is maximum bright position. So all the lamps will glow with maximum brightness. So this is the bright position. Or you may get some other, that is R here, R dash may be here, or R dash may be here, R dash may be here, R dash may be here, somewhere R dash. So only one phase I am comparing. So like that remaining YB also, Y dash, B dash. So you may get some other position like this. Example, I will take another diagram. This is RYB, bus bar 3 phases, and alternator 3 phases. At one instant, suppose like this we got R dash, Y dash, B dash, R dash, Y dash, B dash, like this is there. Now L1 is connected between RR dash, L1, YY dash, L2, BB dash L3. Like this lamps are there. Now in the first position previously here, what is the voltage difference between voltage difference across the lamp? 0. Both are in phase. So as voltage is 0, lamps will not glow, completely dark it is. And here how much voltage? Maximum voltage difference is there, that's why brightness we are getting. And here there is some voltage difference, small voltage difference, maybe some 10 volts, 20 volts, 30 volts like that. So due to that small voltage difference, it has to glow with a little brightness. But there is some property of lamps, whenever the voltages are very low, almost less than 1/3 of rated voltage, then these lamps will not glow at all. These lamps will not glow here. They won't show any brightness. They will show dark only here. But there is some voltage difference or not? Yes. So here important is when we have to close the switch. These switches we have to close, that is alternator should be connected to bus bar at what condition? Whenever these lamps are dark, then only we have to close. Because in dark position only we can say that, exact dark position only we can say that the two systems exactly in phase. Then only we have to close, otherwise circulating current will come. Okay. So we have to close in this position. Here also lamps are dark. In this position also lamps are dark, suppose, complete dark. Then how can you identify which position is exact in phase position? That is the drawback of this method. So in first method, we cannot identify the exact dark position or exact in phase position of both R and R dash, alternator and bus bar phases. Exactly in phase or not, we cannot identify that. That's why it is difficult in this method. That's why we go to second method, 2 lamps equal bright and 1 lamp dark. Now once you got all the lamps are dark or all the lamps are bright, we can say that both are at same frequency and same phase sequence. If phase sequence is different, then lamps will not show equal bright, equal dark. They will show one is dark, remaining 2 will be brighter. If phase sequence is different, you never get that. So you will get this condition only when the two systems having same sequence, same frequency. Suppose frequency of alternator is different than bus bar, then what happened? R by B rotating in the space here at synchronous speed, R dash, Y dash, B dash also rotating at synchronous speed. Suppose if frequency is more, frequency more means the speed of alternator is more, that's why frequency is more, then this R dash, Y dash speed also increases. So after some time R dash will move away from R, maybe at one instant both in phase, no. After some time R dash will go away from R. Then slowly voltage increase, slowly lamp position becomes bright, again it will come near dark. So this is called flickering of lamp. So lamps will flicker here. So lamps flickering means frequency not same. So simply whenever you got this condition, equal bright or equal dark, any one only, you should not get both. You may get equal bright or you may get equal dark continuously. Suppose you observe for 1 minute dark only, 2 minutes dark only, 1 hour also dark only, means exactly they are in phase. Or if you get bright also, bright means they are out of phase. If you get bright position for 2 minutes, you observe same bright is there, after 30 minutes also bright is the same brightness is there, means they are having same frequency, same sequence but out of phase. So we need to get again in phase, means dark position we have to achieve. So there is some process in power plants we use to change that bright position to dark position, because dark position is required for us. So anyhow, in 3 lamps equal bright or dark, it is difficult to achieve exact dark position of lamp, because when there is a slight voltage difference also it is showing, when there is slight voltage difference also it is showing darkness only. Okay, that's why it is difficult to identify exact dark position. That is the drawback of this method. That's why we go to second method. Okay, what is the second method? Second method is 2 lamps equal bright, 2 lamps equal bright and 1 lamp dark. 1 lamp dark. Whenever you got this position in the figure or in the connection, you can say they are exactly in phase, exact dark position it is, exact in phase position. So why it is observed here? Suppose this is R by B, bus bar 3 phases, R, Y, B. Bus bar 3 phases. Next alternator 3 phases, R dash, R dash, Y dash, B dash. So they are in phase only, R dash in phase, Y dash in phase, B dash in phase. Okay, B dash also in phase. Now observe here, this is Y dash. How to connect lamps in this case is, previously how the lamps are connected, see L1 connected between R dash, Y dash, B dash. So this is R, this is Y, this is B. R dash, Y dash, B dash, 3 lamps connected. But just observe here only I am showing. In second connection, if you want 2 lamps equal bright and 1 lamp dark, how to connect these lamps is, only 1 lamp we connect directly. Suppose L1 connected between R dash, and remaining 2 lamps L2 and L3 we don't connect like this. So L2 will be connected between Y and B dash, cross connected. So between Y and B dash L2 connected, and between B and Y dash L3 will be connected. Only 1 lamp we connect between R dash, remaining we have to connect cross, YB dash, BY dash. So like this we have to connect. So L between R dash there is L1, lamp 1 is between R dash, L1 it is. Now where is L2? L2 we connect between YB dash, L2 we connect between YB dash, this is B dash, this is Y, this is L2, and remaining L3 connected between BY dash, L3 connected between BY dash. So like this we have to connect. So after connection of these lamps, observe the lamp position. See here, this L1 between R dash, that's why what is the voltage difference here? 0. So this lamp completely dark. And what about these 2 lamps? See, across L2 there is some voltage difference. They are not in phases, there is some voltage difference. And across L3 also there is some voltage difference. So when there is voltage difference, these lamps will have some brightness. Now these 2 are equal brightness or not? Because equal voltage difference for both. So they will show equal bright. These 2 lamps will be equal bright, and this lamp is completely dark. Once you achieve this condition in the lamps, now you can close alternator to bus bar. Now you may get doubt. Previously you said in dark position we have to close, but here bright position is there, how can you close? So here even they are bright, observe Y dash in phase only, B dash also in phase only. But why these lamps are glowing here? Due to cross connection they are glowing. That's why this is not a problem, because only for our purpose we have connected cross, it is like this. Because previously we have the problem. No? Now whatever the problem is there previously in this diagram. So I said when there is a low voltage difference, these lamps are dark only. Suppose you got this position, L1 is here. Okay, where is L2? L2 is YB dash. L2 is YB dash. YB dash. So here L2 will be there, and here L3 will be there. See, L2, L3 will not glow equal bright. In no other case you get this 2 equal bright, 2 lamps equal bright, 1 lamp dark. You never get in any other position. Only in this position, R dash in phase, Y dash in phase, B dash in phase. Here only you will get. So we can achieve exact in phase position using this method. Okay, that's why we preferred these 2 lamps equal bright and 1 lamp dark. Whenever you got this condition, now you can close alternator to bus bar. So like this we synchronize alternator to bus bar. Okay, so this is the procedure for synchronization of alternator to bus bar using lamp methods. And synchroscope is an instrument. Synchroscope is directly instrument. We connect, compare the frequency of the bus bar and alternator directly. It will show whether frequencies are different or not. If frequencies are same, it will show 0 reading. 0 indicates that both are having at same frequency. Otherwise, it will show some non-zero reading there. Okay. So this is our today's topic, important topic. Now let's see some questions on this. See the question. So these questions overall in synchronous machine, not only on this topic. See the question is, zero power factor method for an alternator is generally used to determine dash. Zero power factor. So what is this? One of the voltage regulation method it is. So voltage regulation we can find by some methods. What are that? Voltage regulation methods. We have synchronous impedance method, ZS method we call, synchronous impedance method, or EMF method we call it. Next, MMF method, next ZPF method, zero power factor method, or also called Portier method, it is Portier method, and one more is ASA method, American Standard Association method. So these are voltage regulation methods. So here question is, ZPF method of an alternator is generally used to determine dash. So why we use ZPF method? To find voltage regulation of alternator. Okay. So to find voltage regulation we use this method, ZPF. So answer is voltage regulation of alternator. So synchronous impedance of alternator we conduct OC test, SC test. So from there we get ZS. Okay. And efficiency of alternator directly by load connection we can find efficiency. So that is wrong. So voltage regulation of alternator is correct, right? Next question. Next one. See this question. Two alternators A and B are sharing the inductive load equally. So two alternators operating in parallel sharing the inductive load equally initially. What will happen when excitation of alternator A is increased? Answer this. What happened when excitation of alternator A is increased? So we have in two alternator parallel operation, change in excitation, change in mechanical input, like the two cases we have. So whenever excitation of alternator A increased, so what happened due to that? Whenever excitation of alternator A is increased, then what will happen? Yes, the answer is, so whenever excitation of any one alternator increases, that is called over excitation. So during that, the current supplied by that particular alternator increase. Current supplied by that particular alternator increased. Suppose if they ask power factor also increases. So there are some conditions here in that two cases, excitation variation and mechanical input variation, go through that once. So whenever excitation of alternator A is increased, the current supplied by the same alternator will increase, because whenever excitation increase, its voltage little bit increase. Then the voltage of this alternator A is more than this alternator. Now it will send some synchronizing circulating current, some extra current. Now when current is moving from this alternator, the current in this branch increases and it is moving opposite to alternator B current. So current in alternator B little bit decreases there. Okay. So current of alternator A will increase, current delivered by A will increase and of B will decrease. So whenever A increase, B will decrease because load is same. Load required 100 amperes. Previously both 50-50 supplying. Now it is supplying 52. Then how much it has to supply? 48 only. So it will decrease, alternator B will decrease. So option A is correct for this, right? Alternator A will increase and B, alternator B current will decrease. Yes, option A is right. Clear? Next question. Next, see this question. In synchronous motor, minimum armature current. So mostly in RRB, JE and SSC, JE, the questions previously we are getting is almost in the same range. Same questions, same model of questions we are getting. Because in this JE exam, most of the questions is theoretical questions, conceptual questions directly. So numerically very less questions we have, mostly theoretical, conceptual. Now see this. In synchronous motor, minimum armature current occurs at dash. So where we get minimum armature current? So given ZPF, zero power factor, leading power factor, lagging power factor, unity power factor. Answer this. What is the answer? The answer is dash. Yes. So if you remember V curve of this synchronous machines, that may be for alternator or synchronous motor, anything, V curve. So V curve will be like this. And here we have This is V curve. So V curve is drawn between which two parameters? Armature current versus field current. So this is armature current. This is at unity power factor. Here the armature current is minimum, and this is we called normal excitation. Wherever we get UPF, inverted V curve is like this. Here we get UPF, maximum power factor is 1. So at unity power factor, armature current will be minimum. This is we call normal excitation. Okay. So for both alternator, generator or motor, same graph it is. With over excitation, lag lead will interchange, remaining is same. So where armature current is minimum, this is armature current, this is power factor variation. So we will get minimum armature current at which power factor? Unity power factor always. So option D is correct. The armature current is minimum at unity power factor. And where it is maximum? Maximum we get at two conditions. This is ZPF synchronous motor. This is leading, over excitation leading, under excitation lagging for synchronous motor. Now where we get maximum? Two conditions we get maximum. ZPF lag and ZPF lag is maximum, ZPF lead also maximum. But minimum armature current only at unity power factor. Right? Next question. See the next question. See this. Voltage regulation of alternator may be negative when dash. So when the voltage regulation will be negative. So when we get this negative voltage regulation. Same concept of this regulation in transformer and alternator. So negative voltage regulation is possible at which power factor? So load power factor is lagging, load power factor is leading. It is loaded beyond its full load capacity. Machine is run at very low loads. So regulation positive, negative, 0 depends on power factors. Mainly depends on power factor and also load. But mainly depends on power factor of loads. So here we have lag lead out of these two. Where we get negative regulation? Remember, for leading power factor only, we will get positive regulation, we will get 0 regulation, we will get negative regulation. For lagging power factor, always positive we get, always positive. But 0 and negative regulation possible only in case of leading. That may be transformer or alternator. So the answer is for the load power factor of leading. When it is leading power factor, we get negative regulation there. Okay, 0 regulation also leading only we get. Okay, next question. Next question. A synchronous motor can be used as synchronous condenser when it is dash. Answer this. A synchronous motor can be used as synchronous condenser. Condenser means capacitor. So when synchronous motor behaves as capacitor, under what condition? What is answer? Answer is, so given over-excited, overloaded, under-excited, overloaded, underloaded. So whether the motor behaves as capacitor or inductor depends on excitation, but not loaded condition. Overloaded, underloaded is not correct. Just it is to confuse. So here a synchronous motor operates as a capacitor under which condition? Over-excited condition. So previously we have seen over-excited motor operates at which power factor? Leading power factor. Under-excited motor operates at lagging power factor. Leading nothing but capacitive nature. So over-excited synchronous motor behaves as capacitor. But is it purely capacitor? That depends on load condition, whether it is underloaded or overloaded or loaded condition. So that depends on this load condition. Over-excited is in capacitive nature, but purely capacitor means it should be under no load condition. Remember here, and over-excited synchronous motor under no load behaves as capacitor or condenser. an overexcited synchronous motor, overexcited synchronous motor under no load behaves as capacitor. Purely capacitor it is, behaves as capacitor or condenser. Suppose if it is loaded condition, then also it is having capacitive nature, but not purely capacitive nature. Resistance will also comes under this. Okay. Now pure capacitor means zero power factor leading, but when it is loaded, then it may act as some 0.2 lead or 0.4 lead, like that. Power factor will change. Okay, but still capacitive nature it is. Next question. Damper winding in synchronous motor is used to dash. Answer. Damper winding in synchronous motors is used for dash. What is answer? To suppress hunting, to improve power factor, to develop reluctance torque, improve the efficiency. So damper winding in case of synchronous motor we use for two purposes. What is the one important purpose of damper winding? One of the starting method. We use damper winding for the purpose of starting, one of the starting method it is, because synchronous motors are not self-start motors. So we need to provide some external method, or one method is in the damper winding. So internally damper windings are copper bars inserted in the pole faces of this rotor and short circuited, just like squirrel cage rotor it looks like. However, squirrel cage induction motor is self-start. Now using damper winding, synchronous motor also will become self-start. And once it reaches synchronous speed, then there is no function of damper winding, because at synchronous speed, relative speed will be 0 between RMF and the rotor speed, relative speed 0. Then these copper bars or damper bars will not cut any flux. No EMF in that, no current, nothing. But here from the options, if you see, to suppress hunting, yes, this is correct. Starting is not given. We use for the purpose of starting and also to eliminate hunting, because hunting not only in alternators, synchronous motors also takes place. Now how to eliminate hunting in synchronous motor? Same damper bars. How we eliminate hunting in alternators? By using damper bars. In the same way, same damper bars we use in case of synchronous motor for starting purpose and also to eliminate hunting in the synchronous motor, that is to suppress hunting. Option A is correct. Option A is right. Okay, and here there is option C, to develop reluctance torque. No. So it is not the main purpose of the damper winding. So damper windings will produce a torque under hunting condition. That torque we called transient torque. That torque may be induction motor torque, that torque may be induction generator torque. So that you will get in hunting topic clearly. Next question. Which of the following condition is not mandatory for alternators working in parallel? Tell me from the options. Which condition is not mandatory or necessary to operate in parallel? Just now we have seen have equal kVA. So this condition is not necessary condition, not required, not at all, because an alternator of 100 MVA, an alternator of 20 MVA, you can operate in parallel. Just like transformer also, you can see transformers outside. Is all the transformers in your streets nearby are having same sizes or same capacities? No. One will be small, one will be large. So rating, kVA rating of transformers or kVA rating of alternators or volt ampere rating may be anything. This is not necessary. Only voltage rating, phase sequence and frequency. These three only the conditions, not this one. So answer is C here. Which is not mandatory means kVA rating is not mandatory for parallel operation. Okay, next. The reactive power generated by synchronous synchronous alternator can be controlled by dash. Reactive power. So in alternators, what is the rating of alternator generally in complex power? Volt ampere. The rating of alternators will be in complex power or apparent power, which is the sum of active and reactive powers. Which is the sum of active and reactive power. Now from this, there is active power and reactive power both in generators or alternators. If you want to control particularly reactive power of alternator, which one we have to change? Similarly, in order to change active power of alternator, which one we have to change mainly? So we have in alternator mainly two variations. One is excitation variation and mechanical input variation, turbine input. So whenever you want to change reactive power related to mainly flux in the alternator, flux in the machine. That flux mainly we can change by which of these here? Changing alternator speed? No. Changing field excitation, changing terminal voltage. Terminal voltage directly we cannot change. That depends on again excitation. Next, changing prime mover input. These two are same. Okay. So here answer will be option B. Option B is correct. By changing field excitation. So whenever field excitation changes, flux will change, and that will change the reactive power of alternator mainly. Okay. So if you want to change the reactive power in alternators, which one we have to change mainly? Excitation of alternator we have to change. To change the reactive power, change the excitation. Active power also will change here, but that is negligible change. Next, if you want to change active power of alternator mainly, which one we have to change? Then we have to change this prime mover input or mechanical input. Prime mover input we have to change. Okay. So with the prime mover input variation, active power of alternator mainly changes, and with the change in excitation, reactive power of alternators mainly will change. Clear? So answer is option B, changing field excitation. See the next question. Synchronous impedance method of finding voltage regulation of an alternator is called pessimistic method. So previously I mentioned what are the methods to find voltage regulation? We have EMF method, synchronous impedance method we call it, MMF method, and ZPF method, ASA method. So out of these, synchronous impedance method or EMF method is called as pessimistic method, and MMF method is called as optimistic method, because this synchronous impedance method will give the regulation more than the actual regulation. Suppose actual regulation of alternator with the loading condition we got 25%. But if you find regulation using this synchronous impedance method, we have some procedure for that. By drawing OCC, SCC in the graph, we will find ZS and then EMF and then regulation. So if you find like that, we are getting, suppose actually is 25 we taken, but we will get 30% for example. Means more than that we get. But if you find the same regulation of alternator using MMF method, we will get some less than 25, let 20% only. Lowest we are getting. But synchronous impedance method is giving highest value, that is 30% we got. So because of that reason, we called synchronous impedance method is a pessimistic method, since it provides the voltage regulation more than its actual voltage regulation. More than that actual regulation. That's why pessimistic nature it is. But MMF method will give less than actual. That is optimistic nature. That's why we call MMF method is optimistic method. But ZPF method is accurate method. It will give the regulation almost very near to that. And ASA method is the most accurate method. Very near to true accurate or very near to actual regulation. ASA method. And ZPF will give near to that. But this MMF and EMF method will give so much deviation. One is very high, one is very low. That's why the method which gives high regulation we call pessimistic, and which give low regulation we call optimistic. Now, synchronous impedance method of finding voltage regulation of an alternator is called pessimistic. Because why we call pessimistic? Because it gives high regulation. No? It gives value lower? No. Armature reaction wholly magnetizing? No. It is simple to perform? No. It gives regulation value higher than its actual regulation. Okay, it gives regulation higher than actual value. That's why we call pessimistic it is. Okay. Clear it is? So this is our today's topic and some questions on this synchronous machines. Okay. Now you need to just practice the questions mostly before examination from previous.